Good afternoon. First of all, thank you so much for the organizers to allow me to give this talk and to hold this conference. It's been very easy to follow online, and I've been learning a lot. But also, I'm a bit sad to not be there physically, but it happens. Anyway, my name is Arief Ahmad. I'm a PhD student at Uppsala University, Sweden, and today I will be talking a bit more about what I'm currently doing in terms of work, and it's about multimode pulsations in AGB stars, in particular, what we have been doing in the 3D side. I will start off by showing the OGLE database. So it is a catalog of variable stars. So you have different variable stars over there, and it is essentially a period luminosity plot with the width and height index on the y-axis. For the stars that we are particularly interested in is the semi-regular variables and the Miras. And for each individual star in this plot, it can appear in different places depending on the observed pulsation modes. So to be more explicit in this, these are a mixture of radial and non-radial pulsation modes. And within the radial mode, you have the fundamental and overtones. As to why it may be interesting, or it is interesting to look into this, is because the timescales involved in the pulsations and any variability will introduce some changes in the chemistry. So, convection and pulsations interact with each other, and it can affect the chemistry of the atmosphere. And we know the dust process formation, the dust formation process is related to the pulsations, of course, and this directly affects the mass loss rates. And the pulsation modes being displayed can also tell you about its evolution along the AGB, or in general, its process in the stellar evolution. Just to touch on the multi-period pulsations in terms of the modeling aspects. So in one dimension, it would involve solving the linearized stellar pulsation equations. There's been years of developments in this, and importantly for AGB stars, there have been advancements in linear and nonlinear pulsation models, for example, Trabucchi in 2021 and other references in there. In general, and more commonly used in astroseismology are these stellar oscillation codes, for example, the gyro code, which we've heard a bit on today. In any case, in 1D, you would tend to have an input stellar model, and then you calculate the eigenfrequencies, which gives you the possible pulsation modes or periods within the star. So the question actually now becomes for us is, in 3D, could we actually reproduce these multi-period pulsations, and could it emerge naturally in our simulations? To describe what we've been doing is we've been using the Cobalt code, which you've heard on Monday and a bit on yesterday. But to introduce you again, it is a 3D radiation hydrodynamics code. We treat the star by putting it in a box. So it's a global star in a box type of simulation. And perhaps the most important difference between 1D and 3D in this case is that convection is an emergent property in the sense that we've not applied any parameterizations or any special treatment on the convection, and that it emerges naturally from the radiation and hydrodynamics. Thus far, we've only been able to study the self-excited pulsations, but only in the radial fundamental mode. So these are two papers that have been investigating this. But again, what we've studied so far, or been able to study so far, are the pulsations in the radial fundamental mode. And to illustrate our recent efforts in terms of modeling AGB stars, I show you a previous model grid of our AGB stars. So this is just the luminosity and effective temperature plot. And maybe from last year and throughout the years, we've been producing 1.5 solar masses models. So these are the current stellar mass. But over the past 8 months or so, we've been producing a newer grid of models. So in the triangles here, so you can see we are explicitly trying to expand the parameter space. In this case, we are intentionally going towards denser AGB stars, so lower luminosity and higher effective temperature stars. And after a brief investigation, we decided to fix a core mass of 0.6 solar mass. So this is the mass of the white dwarf in the center of the star. And what we can do on all the simulations is to apply the fast Fourier transform to identify the pulsation behaviors. And so typical in the very luminous models in the top right in the figure here, if you apply a FFT, the fast Fourier transform, you will get a spectrum like this. So it's normalized power on the y-axis and time in this case on the x-axis. So typical or characteristic of the models here, you would get a strong singular peak, but it's sort of very spread out. And this is in the radial fundamental mode. As you go further down, you will get something typical like this. So the radial fundamental mode is still appearing, but in this case, you can really see a prominent signal in the lower time scales here, and this is the first radial overtone mode. So to very quickly answer my question before, yes, we actually do see higher order pulsation modes lower down or towards denser AGB stars. So that's a spoiler. Here is a very busy plot, but it is still a period luminosity plot. But the colors now is the intensity of the FFT power. On the y-axis, so each row, for example, is a different model depending on its luminosity. So yeah, this is a busy plot, but let's go through it maybe. And so at the very luminous area, you would get, like I mentioned before, a very spread out peak. So you can sort of see it here. In this case, the pulsation amplitude in terms of the bolometric band is roughly around 0.2 magnitude. As you go further down in the middle, in this case, overtones begin to appear. And the pulsation amplitude is roughly around 0.1. So it's going down in terms of amplitude. And going even further to the denser AGB stars that we have, you can really see the higher overtones. And again, it follows the trend that the pulsation amplitude decreases. And to show you clearer about the radial overtones, I've made these sketches. So n equals 0 is the radial fundamental mode. You can see this ridge, and then you can see the first overtone ridge, which is this one, and then the second overtone in this shape. And you may notice within each ridge you have these splittings, and these are signals of the non-radial modes that we see from the models. And so these are nodes on the surface of the star, and if you're familiar with, it's related to the quantum numbers L and M. And this is an interesting property that we want to investigate further in terms of their behavior, of course. So this is also quite exciting for us. Another important behavior is this dominant mode switch. So if you zoom in again, you can see higher up in the luminous models, they tend to peak in the radial fundamental mode. But as you go towards denser stars, you can switch between being pulsating dominantly in the radial fundamental mode into the overtone mode now. So this switch is quite interesting and may have consequences in terms of wanting to understand the stellar evolution. So we can try to explain this mode switch. For example, this is a qualitative suggestion or what we can see. So the plots on the left is the convective speed as a function of the stellar radius for the different luminosity sequence for the one solar mass AGB model. And on the right is a sound speed as a function again of the stellar radius. The primary difference between the luminosities here is the density within the star, and the density in this case affects convective and sound speeds. But if you look closer into this small region here, well, not small, but roughly around 50% of this region here, the convective timescales, if you compare the numbers here and the numbers of the sound speed in this region, begin to become similar. So in this case, convective timescales can compete with the sound speed timescales, which is also related to the pulsation timescales. And what can happen is the fluctuations by the convection may align or may be in sync with the pulsation periods and create like a resonance and cavity effect. And actually this interaction influences the amplitude of the different pulsation modes. And it can play around with the density as well to create which pulsation mode is dominating in terms of the pulsation behavior. So that is one qualitative thing that we can do, but we can also approach it quantitatively. So here is another period luminosity plot, but this time we have categorized or quantified the pulsation periods. So in circles and enclosed in the colors is the power fraction of the FFT spectrum. So in circles is when the fundamental mode is dominating in the pulsations, and in squares is when the overtone begins to dominate. And as you've seen before, it sort of separates nicely in the middle here. And this mode switch is good to be quantifiable or we're trying to understand it better. What we can also do is to compare our new models with our previous models. In this case, I've overplotted the prediction of the period if it were to follow a period mean density relation derived from our previous models. So one of our papers from last year. And you can see the prediction is slightly consistently offset between the prediction and the radial fundamental mode that we are seeing here. One way to interpret this is that we're seeing the effect of a different mass distribution in the star. And if you recall correctly, I mentioned we are fixing the core mass of 0.6 solar mass for the new models, whereas for the previous models, it might be slightly higher. So this could explain, or probably explains, why we see this consistent offset. We, of course, can use any further results from this. And one example is, or will be given to you by Emily after the tea break. So just an advertisement where she will give us or let us know about what she's been doing in terms of using results from the 3D and seeing how it affects other aspects of different models. And we can also use these pulsation periods to investigate the physical properties of the star. In this case, I overplotted the plus signs, which is the timescales following the cutoff frequency if you consider the stellar structure of the star. One important bit here is that the cutoff frequency provides you the minimum pulsation period timescales. So theoretically, what should be stable in the star. And you can see, especially for the more luminous models, at least, the overtones or the second pulsation mode detected is below the minimum. And so this primarily tells us that what the algorithm is detecting could be not an overtone necessarily, but a higher harmonics of the radial fundamental mode. Yep. So that is what I have to say. I know it's a fairly simple talk, but it's mainly to highlight that for our new sequence of models, we are beginning to see overtones and non-radial modes, which is very exciting. Of course, we're doing various investigations to look at what we can obtain. But the interplay between convection and pulsations, of course, complicate the picture considerably, but we know some ideas on what to pursue. And the 3D results, of course, could or should be used into other models and see how a more natural treatment of convection can differ in terms of what it says about other predicted properties of stars, AGB stars. Otherwise, thank you so much for your attention. I appreciate you listening to me.
Hi, Arief. Really nice talk. I'm just curious whether you have any insights or comments about the long secondary periods that are seen around AGB stars.
Yeah. Hello, Amanda. Nice to hear from you. We do, in very special cases, our models do display a long secondary period. This is heavily tied to the convection, and sometimes it makes the whole star very dim, and it stays dim for a long while, and then recovers its original intended luminosity, and it can happen periodically. But the issue with this, like you said, like we're talking about long secondary periods, it requires long simulation times to really identify the LSP periods. So for the special models, we just need to run them longer to look at them more conclusively.
Hi, is there any way to use these models to predict the effect of companions, say low mass companions, even planets, which are outside the envelopes? They're interacting maybe tidally, and would probably whatever they induce would interplay with the pulsation of the star itself, and so to find a way to detect these planets or even low mass companions.
Not right now, because what we're doing now is treating single stars. One way to investigate that, though, is we've seen a lot of very interesting binary simulations, SPH, and all that stuff. One way to incorporate this is to perhaps put in or explore the pulsation parameters being input into the binary system. But currently with Cobalt, we can't do this companion stuff.
Thank you.
Hi, thanks for the great talk. I was wondering if you have made any comparisons or plan to make any comparisons to linear pulsation models that exist in the literature, and if there are any consistency between your models and those.
Yeah, that's actually what I'm trying to do right now, but I would have to convert the Cobalt data into a similar input data form to input into the pulsation models. A different way is to, of course, take a grid of models and try to interpolate the Cobalt models into that data grid. But yes, this should be done to check for any differences, and one that we're looking to do.
Yeah, thank you. I think there's the Tribucci grid of models that might be
Yeah,
interesting to compare to.
yeah,
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 exactly.
perfect. Yeah,
Yeah.
thanks.